Okay, so again, remember we have 6 degrees of freedom, so we're going down this far left-hand column, and we want to keep going until we reach a critical value that is under 0.05, which is our cutoff, and that's 1.9 here, 1.943. But if you remember, if you look up here, our t-value was only 1.0, okay? So we know right away that we're not able to reject our null hypothesis. But let's find out exactly where our p-value is. So our t-value of 1 fits right in between this column, between 0.718 and 1.440. And those two numbers, respectively, are under the p-value columns of 0.25 and 0.1. Okay? So we can say that our p-value is going to be, what is it? It's going to be less than 0.25, but greater than 0.1, okay? Now, what's our p-value? Well, I was actually talking about it earlier. You just may not have caught what I said. If you look down here, our p-value is just where on these tails, it's where your t-value is along this hypothetical null distribution. Okay, so really, we had to get past 0.05, either this point or further to the right, in order to declare statistical significance. But since we're between this range, our t-value is actually going to have a probability somewhere between 0.25 and 0.1. So it's going to be somewhere in here, right? And because, you know, a t-value occurring anywhere from 25% of the time to 10% of the time is thought by the scientific community to not be very unlikely. So again, this distribution assumes that H null is true, and because this is not a very unlikely occurrence, 25% of the time to 10% of the time, we will therefore, let's see, our conclusion is we fail to reject the null, right? Now, if you come back here to the t-distribution table, let's say we had a t-value of, let's say 2.5 with the same number of degrees of freedom, okay? So the same total number of data points. If we had a t-value of 2.5, we keep going to the right, okay? We go past 0.05, okay? So right away, we know that we can now reject the null hypothesis. And then the next column over is 2.447. We still haven't reached 2.5. And then we go, okay, here, this column 3.143, which is under the p-value 0.01, we now know that we have a p-value somewhere between 0.025 and 0.01. In this case, we would reject the null, right? Now, let's go back to our original t-value of 1.0, but let's instead assume that instead of a one-tailed hypothesis, we had made a two-tailed hypothesis. What's the difference? Well, a one-tailed hypothesis, if you look back up here, merely specifies the direction of difference between treatment X and treatment Y. It states a one-tailed hypothesis in this case would have to say, okay, either treatment Y is greater than treatment X or treatment X is greater than treatment Y. It has to specify some sort of directional data trend. Again, either Y is greater than X or the opposite. Yeah, one or the other. A two-tailed hypothesis is more vague. All right, it's more of a hedging your bet. And so a two-tailed hypothesis would be merely that treatment Y is not equal to treatment X. It's not stating whether one is bigger or less than the other. It's just stating that they're different. So if you go back to the this illustration of the null distribution, basically you're testing on both ends. You're testing the probabilities of both tails of the null distribution. Okay, you're both testing that Y may be greater than X, or that X may be greater than Y. Okay, and so please note that if we were to use the same exact cutoff of 0.05 here, if we were to use the same null distribution chart as for a one-tailed hypothesis as we would for a two-tailed hypothesis, note that if we filled in the gaps here, let's say we happen to get a p-value of 0.05 or more extreme on this one-tailed chart here, note if we were checking the probabilities at both ends of the tails, we'd actually have a true probability 0.05 plus 0.05 of 0.10, okay? And that's not really fair, for lack of a better word. So if you do make a purposely vague, more of a hedged bet with a two-tailed hypothesis, and you're only stating that treatment Y is greater than treatment X, or if you go back to our example here, if you're just saying that, okay, most men and our male and female treatments will have unequal heights, basically. If you're going to be that vague, then you have to go back down to this null distribution table, which again, you note that in your books, it's only shaded in at one tail, which means that this distribution table and chart is built for a one-tailed hypothesis. That means you have to then adjust this, okay, kind of in your head. So you go back down to this p-value, these p-value rows in bold here. You have to then double them. 0.4 for a two-tailed hypothesis becomes 0.8, 0.25 becomes 0.50, 0.1 becomes 0.2, then 0.1, 0.05, and so on, okay? And otherwise, you use the chart exactly the same as you would for one-tailed hypothesis. You just have to adjust these p-values to basically account for the fact that you're testing both ends of a null distribution chart, okay? But again, because our t-value of 1.0 was not rejected under the one-tailed hypothesis, let's see if a two-tailed hypothesis work. Go back down to 6 degrees of freedom, right? All the way to 1. Nope, in fact, it'd be even weaker, right? Because this t-value would be, or this p-value would be 0.2. So in either case, whether we're testing this with a one-tailed hypothesis or a two-tailed hypothesis, we fail to reject the null. Now, if you go back up here to our main hypotheses, please note that in statistics, we're never proving or disproving the alternative hypothesis, right? You're only rejecting or failing to reject the null. And that's it.